This is a summary of design with natural processes and what the principles are. So there are 5 principles. One is that you design with waste materials, so that you're designing like nature. You use very little transportation. You use inexpensive materials, that's number 1. Number 2, you self-repair. 3, you self-sense. 4, you recycle yourself. And 5, you improve the environment for other organisms or other buildings or whatever. So the first one is the first example, and all of these were made at large scales with companies. So they're not just, ideas, but I'm just showing you examples of things from the lab. So this one is using fly ash. The reason you want to use fly ash is because it's a waste product from coal and it has heavy metals and radioactive materials in it. And so we made very large panels with a company in Chicago in which we made them out of fly ash, which is the darker material, or in some cases we made them as a sandwich panel with bottom ash as well. So this is the very light fly ash, this is the darker fly ash, but this is fly ash, which is bottom ash with fly ash in the middle. And then we did a lot of work on using the fly ash, which is actually little tiny glass beads, hollow, making those into insulation. So that's number 1, using a waste material and improving its use, because in this case you sequester the heavy metals in a building material and so it doesn't leach into the groundwater. Okay, number 2 is self-repair. I did lots of work on invented self-repairing concrete. The reason to do self-repairing concrete is because the making of cement releases 6 to 8% of the world's CO2. So if you can make it self-repair, you use much less of the material and produce much less of it. And so these represent bridges, these models, and we put the repair stuff in at the important joints. And you can see that this one got more damaged than that one, although I have better examples of that. And then these are polymer composite versions of the same thing, and you can see the self-repairing chemical in the veins of the structure. So one of the problems with concrete is that it corrodes, so we were able to put some anti-corrosion chemical right next to the rebar and test it in the standard tests that they use and show that there was less corrosion and the onset of corrosion was delayed. Okay, so we made lots of samples like this and like this. And so that's number 2. Number 3, which I don't have a lot of examples of right now, is self-repair, but self-sensing, but you can do self-sensing with a variety of ways, with X-ray, with ultrasound, with fiber optics, and we did all of that, and it's in the papers that are on this subject. Then we started to work, this project was done with the Highway Department, with the National, the Transportation Research Board and the National Academy of Sciences. Then we got a project with the Air Force to do self-repairing polymer composites for airplane wings, and there the environmental idea is that if you can use these materials that self-repair, then you can make a thinner wing because you don't have to have extra safety measures by adding extra layers. So we added very tiny little repair tubes, and the testing, a lot of it was done with an impact and then compression. So it's called compression after impact, which is kind of the name of the game in the aerospace industry. And also we did these large samples to talk about whether it would act well in shear, which it did. We also made these materials, which you can see there, which are to represent airplane wings, and tested those. Then again, still in self-repairing composites, we did a project. This time it was for the Army, and it was, as you can see in that poster up there, we were doing self-repairing composite panels, and we shot them to show that they could self-repair, especially when you got the shots close to each other. You could really see the self-repair material. And then if you focus over on that poster over there, you can see that we, on the right hand side, we actually blasted these panels and tested them. So we're down to self-repair, self-sensing. And then in terms of recycling, we did a project which is not represented here, but with another company, in which we were able to show that you could demolish girders which had high pressure tendons inside, pieces of metal that were pulled at great pressure, and you could, instead of having one place that would, if you cut it, it would release huge amounts of energy, and these tendons could fly for blocks, very powerful. But if you could have them cut at little increments by having our self-repairing materials at different places, then you would reduce the pressure a lot. It's kind of like if you're going to have a big long rubber band and you cut it in the middle, there's a lot of energy, whereas if you make that rubber band into shorter segments, there's less energy. And then finally, in terms of improving the environment, we did a project on self-repairing and concrete that self-repairs the underlying concrete by absorbing CO2 and releasing oxygen. And we did a lot of work on this and showed that you can take a lot of CO2, and at the same time you can increase the strength of the concrete. So again, these are projects that have been funded and were done with large-scale companies and to demonstrate them. And so this, in summary, building with natural process means that you build with materials that are available cheap, you self-sense, self-repair, recycle yourself, and improve the environment.